What do chemical engineers actually do? Are they just chemists in hard hats or mini versions of Walter White from Breaking Bad? Not quite. In reality, chemical engineering is one of the most versatile fields you can study. It can take you everywhere, from designing medicines to producing clean energy, from food manufacturing to even space exploration. Today, we'll break down what you study in a chemical engineering bachelor's degree, what careers it opens up, what the job market looks like in academia and industry, and where the future of this field is headed. Let's start with the basics. What do you actually study as a chemical engineering undergraduate? A chemical engineering degree combines chemistry, physics, and mathematics. But the real magic happens when you apply these sciences to design processes. Think of it like cooking, but on an industrial scale. Instead of making one loaf of bread, you're designing the process to feed an entire city. So, what are the main areas you'll study? First up, mass and energy balances. This is the accounting system of matter and energy. Nothing disappears. Nothing is created out of thin air. It all has to balance. You'll learn how to write equations that track every input and output of a process. Imagine a soda factory. You'll calculate exactly how much water, sugar, and carbon dioxide go in, and how much soda and extra heat comes out. This is the foundation for everything else. Next is thermodynamics. It's the study of energy, how it moves, why heat flows, and why some reactions happen while others don't. Think about why ice melts in summer, or why fuel burns in a car engine. Thermodynamics explains those processes and helps engineers design more efficient systems. Then there's fluid mechanics and heat transfer. This is all about how liquids and gases move and how heat travels. Picture water rushing through a pipe or steam rising from a kettle. Engineers need to know how fast, how much pressure, and how to move fluids safely. And with heat transfer, it's about how to heat things up or cool them down, like designing the cooling system of a car or an industrial refrigerator. Now, chemical reaction engineering. Here, you study how to build reactors, the heart of chemical plants. Imagine making aspirin. In a lab, you can mix chemicals in a flask, but how do you make tons of it safely every single day? Reaction engineering helps you scale up lab chemistry into industrial production. After that, separation processes. Most products don't come out pure. You need to separate them. Think about turning salty seawater into fresh water, or separating oxygen from air for hospitals. Techniques like distillation, membranes, and absorption all come from this area. Then there's process control and safety. Chemical plants are like living systems. They need constant monitoring. Process control is like autopilot. It keeps temperature, pressure, and flow rates steady. And of course, you'll also learn how to prevent accidents and keep everything safe. Next, mathematical modeling and simulation. This is where chemical engineers turn ideas into virtual reality. You'll learn how to build mathematical models of processes and test them in simulators like Aspen Plus and COMSOL, or using a high-performance programming language like MATLAB before building anything in real life. This saves millions of dollars and helps optimize efficiency. And yes, artificial intelligence and machine learning. The future of engineering isn't just pipes and valves, it's data. You can learn how artificial intelligence can analyze massive data sets, predict system behavior, and even control plants in real time. For example, artificial intelligence can optimize a refinery's energy use or help design new materials faster than ever before. Finally, there are electives and emerging topics. Depending on your university, you might dive into biotechnology, renewable energy, nanomaterials, or environmental systems. You'll learn how to design bioreactors for vaccines, create sustainable plastics, or develop processes for hydrogen and battery technologies. By the end of your degree, you're not just a scientist, you're a problem solver who can take science from the test tube and scale it up to serve entire cities or even entire industries. So, what can you actually do with a chemical engineering degree? The beauty of this field is that it's not just about where you work, but also how you work. You might work in a lab, developing new catalysts, testing materials, formulating drugs, or experimenting with sustainable plastics. You might go into process and equipment design, working on reactors, distillation columns, or heat exchangers, often using simulation tools to model entire plants. Or you might focus on artificial intelligence and data-driven roles, applying machine learning to optimize plants, predict failures, or even design brand new materials. And the industries? They're vast: energy and petrochemicals, pharmaceuticals and biotech, food and consumer goods, materials and electronics, environment and sustainability. If you go further into a master's or PhD, you can move into academia or advanced research. That might mean inventing new reactor concepts, developing advanced carbon capture, or pioneering sustainable materials. Academic careers usually involve teaching, publishing research, and leading collaborations. The payoff? You help shape the technologies of the future. And don't forget consulting and cross-disciplinary roles. Chemical engineers often move into management consulting, finance, or policy because they're trained to analyze complex problems logically. So whether you see yourself in the lab, designing equipment, coding AI models, or advising governments, you'll find a path that fits your skills and passions. What about the job market? Let's break it down by role. Lab and research roles are steady and rewarding. You'll get hands-on with innovation, but salaries often start moderate compared to design or consulting. Process and equipment design engineers are in high demand. These jobs pay well because mistakes at this scale cost millions. Artificial intelligence, data, and simulation roles are the fastest growing segment. Engineers who can combine chemical knowledge with digital tools are rare and very well paid. Academia and research careers are more competitive. You'll need at least a master's or PhD. Salaries may be lower, but you get freedom to create new knowledge and lead long-term projects, especially in energy, sustainability, and materials. Consulting and cross-disciplinary roles offer high salaries, but also high pressure. Many chemical engineers thrive here because of their problem-solving mindset. Overall, chemical engineers consistently rank among the highest paid engineering graduates worldwide. Traditional oil and gas jobs are stable but slowing. The strongest growth is in renewable energy, biotech, pharmaceuticals, and digitalization. And adding skills in artificial intelligence and simulation makes you extremely competitive. And now, the future. Chemical engineering is evolving fast. It's about sustainable development, redesigning processes to cut emissions, recycle waste, and create circular economies. It's about the energy transition, hydrogen, carbon capture, and electrified plants. It's about digital twins, building entire factories virtually before installing a single pipe. It's about artificial intelligence, optimizing processes, predicting failures, and discovering new materials. And it's about biotechnology and food security, from lab-grown meat to bio-based plastics and engineered enzymes. In short, chemical engineers aren't just working in refineries anymore, they're leading the charge toward a sustainable, digital, and resilient future. So here's the bottom line. A bachelor's in chemical engineering gives you one of the most versatile toolkits any engineer can have. You'll learn to take science and scale it up, mastering everything from thermodynamics to artificial intelligence. And whether you choose lab research, process design, consulting, or data science, you'll be at the center of solving humanity's toughest challenges. If this gave you a clearer picture of chemical engineering, hit that like button, share your thoughts in the comments, and don't forget to subscribe for more science explained in minutes. See you next time.